Good morning, afternoon, night, whatever it is. Welcome to, we'll call it lecture 23, and we'll call it April 15, 2020. Today we talk about shapes. So by the time we're done today, you're going to be able to basically predict the shape of a molecule from its formula. The process starts with Lewis structures, which you already know, and then uses this new thing we're going to call Vesper theory to accurately predict the shapes of simple one-center molecules. And then you're going to tell me if they're polar or not, and more on that in a bit. So by the time we're done, you're going to be able to tell me that sulfur dioxide has this particular shape, sulfur trioxide has this particular shape, and that sulfur dioxide is polar, and that sulfur trioxide is not polar. All right, so let's get to it. Vesper theory, valence shell electron pair repulsion theory. And this is an incredibly simple and elegant theory that does a very good job of explaining the overall shapes that molecules take. So let's talk about shape. Now, in general, molecular shapes are not commonly known or talked about. But if there's one molecular shape that the average person, much less the average chemistry student, can identify, it's actually this one. So can you tell me what this molecule is? Don't feel bad, almost no one can, at least not right away. This little demonstration also shows the importance of perspective. So let me rotate this molecule 180 degrees. Now do you recognize it? All right, that is in fact, it's actually two molecules, and it is two strands of DNA. So what I showed you before was what the helix looks like. Helix looks like looking down, and this is looking at it from the side. So let's talk about shapes. So we'll start simple because that usually is a good place to start. Just shout it if you know it. Yes, that is a square. What about this one? And if you guess triangle, you are doing good. What about this? So this is not a sphere. It is technically an interlocking series, or a series of interlocked flat pentagons and hexagons. So each of these 5 or 6 membered faces is actually flat. Now if you inflate it and you put it some air, you can kind of get some curvature to it, but this is the basic pattern that goes into your average soccer ball. So there's no know what this shape is. Now at some point, someone might try to tell you in a very smart aleck way that this is an icosahedron, but they are wrong. And you can be even more of a smart aleck and say, no, you are incorrect. The soccer ball shape is in fact a truncated icosahedron. An icosahedron also has a series of interlocking pentagons and hexagons, but it is larger than this one is. Moving on. What about this? And no, butterfly is not a shape. It might look like a d orbital that we talked about. This form, and I think in roughly 20 years of asking questions similar to this, I think 2 people have known what this form is. It's actually called a quatrefoil, which means 4 lobes. And one more. How about that? Now, some of you are probably thinking pyramid shape, and with good reason. Most building pyramids, though, actually don't look like this. If this were laying flat on the ground, you know, there would be 3 faces coming out of the ground. So, you know, wall 1, wall 2, and wall 3 is back here. Most building pyramids, I can just sketch one here for you, actually are square at the bottom. So the bottom looks like this, and then there's a whole bunch of faces that come up like that. So that is technically not a pyramid, although it kind of looks like one. It is called a tetrahedron. It gets that name because tetra, it's got 4 faces. The 3 walls that I talked about, and then the one that would be on the ground. All right. Now this one is kind of important because this one is serious now. It's actually a shape that molecules adopt. Like this. So here's our generic tetrahedron right here. And it turns out that if you look carefully at, let's say, a carbon tetrachloride molecule, that the angles that you see in the molecule are exactly the angles that you see for the faces in a tetrahedron, and that the 4 chlorine atoms, so 1, 2, 3, 4, actually are at the apices of the 4 faces of a tetrahedron. The carbon is somewhere in the middle. So that's a molecular shape. Why do you care? Because the chemical activity of something is actually determined by its structure, by its 3-dimensional shape. And most chemists, most people that are professional chemists, either spend most of their working days either trying to make a molecule that is a specific shape, which should have a specific property, or try to determine the shape of a molecule that they know has a specific property. So either direction is kind of what they usually do. And again, just to hit home this point, chemical reactivity is determined by the structure, and the structure is everything. Now, I had some pre-lecture videos that kind of shows you how we determine what the structure is. Take a look at those, and then you can come back and we can go over these chemical structures now.